Pourbaix diagram. The Pourbaix diagrams are an extremely important tool used in electrochemistry for different reasons. It could be extremely interesting, for instance, for the study of corrosion, or even for comparisons of electrode and also the design of battery. But what is a Pourbaix diagram? A Pourbaix diagram is a thermodynamic plot. This means that we can observe from this diagram only thermodynamics information. And all the data collected, we will see which types of data, are referring to a situation that is thermodynamically reversible in an open circuit condition. And so any types of information regarding how much the process is going fast, so the kinetics, are not present in a Pourbaix diagram. But what is actually a Pourbaix diagram? A Pourbaix diagram is a diagram of the potential versus the pH. But what type of potential? This potential is the reduction potential associated with a specific semi-reaction. So a specific redox reaction, a specific redox couple. So we need to look at some example in order to understand. But what is important to know is that this potential is a reduction potential, and is a reduction potential in open circuit condition. So we are looking about potential that are basically in conditions in which the current is not actually real flowing, as in the case of the zinc oxide, the zinc oxidation that we have described in order to analyze thermodynamics in one of the last videos. So basically, when we are speaking about Pourbaix diagram, we are speaking about diagrams that are referred always with respect to water. What does it mean? That in every type of Pourbaix diagram we can observe the line of water. But what does it mean, the line of water? So, at the very beginning, it's important to say that the Pourbaix diagram is a diagram of state. So, since this is a diagram of state, each single point of the diagrams gives us information about the system. And this is useful because it allows us to understand, for instance, for a specific potential and a specific pH, what it could be the state of the system. If, for instance, our Pourbaix diagrams is the Pourbaix diagram of the zinc or another metal, these state diagrams, this diagram of state, allow us to understand if in this condition maybe the zinc is oxidized, so is present is a zinc 2 plus, or maybe in this point is present a metallic zinc, and so in which way the pH is able to affect the stability expressed in terms of potential. Because we know that higher the potential of a certain species, of a certain redox couple, it means that higher the tendency to be reduced with respect, lower the potential, higher the tendency to be oxidized. So understand in which way the potentials can change due to the pH allow us to understand in which way the stability of the species can change due to the pH. So thermal potentials give us information about the stability, and it is important to know the stability even in different pH scale. So this is a theorem of state. And so we can start with the descriptions of the water line that are always present. But this is a diagram of state. So we have a zone representing the stability of certain species. But obviously in a diagram of state we have some line defining the equilibrium, the passage between maybe one state and the other. So if we have something like this, for instance, maybe this line, we can have that under this zone we have the stability of zinc as metallic zinc, and here we can have the stability of I don't know, zinc 2 plus. Or in general, we can have a generic species A and an oxidized species here. So we are able to define the stability of this species toward the oxidation, maybe, just by looking at the value of potential. But maybe when we are reaching higher pH, what is happening is that this line decreases, and so the oxidation range is extended. And what does it mean? That in this value of pH, for instance, the stability is significantly reduced in terms of resistance versus oxidation. This is the point. And in general, in Pourbaix theorem, always we are able to observe the line of water. So, the line of water. But what is a line in the Pourbaix diagram? The line is the equilibrium between two zones of stabilities concerning different species. For instance, this line is the equilibrium between the existence of A and H2 plus, as in the previous case. So, what is a line in the Pourbaix diagram is the Nernst equation. All the line, or not all obviously, but basically more or less all the line present in a Pourbaix theorem are Nernst equation, solved as a function. What does it mean? Let's imagine to consider the reduction reaction of hydrogen. So H plus 1 electron to give this. We know that this is a redox reaction. We have a redox couple, and this is obviously a similar reaction. In this case, with toward a reduction as a convention. So we can say that in according with the Nernst equation, we have that the potential is equal to the potential in standard condition. So standard condition, we need to remember our condition in which the pH is equal to 0, the temperature is 25 Celsius degree, and the pressure is 1 bar. In general, the Pourbaix diagram are always referring to a temperature that is 25 Celsius degree and the pressure that is 1 bar. And this means that at this point, since we need also to have a pH equal to 0 in standard condition, it means that it represents each single point on this axis. It's quite simple. It's basically something that is quite similar to a straight line. We'll see this in a moment. So we have this plus this, and we have obviously plus RT and F ln H plus square, because we are basically doing this, and P of H2 versus reference, because the activity of gaseous species is expressed in terms of partial pressure, obviously, and not as in basically species in solution. So if we solve this type of equation, we can appreciate that E is still remain equal to E0 minus 0.059 pH. Why pH? Because it's interesting to appreciate that the activity of H plus, is equal to minus logarithm of pH. No, sorry. The pH is equal to minus logarithm 10 days of the activity of H plus. And so what does it mean? That if we are able at the very beginning to transform this logarithm in logarithm in base 10, we are able to solve these equations and obtain this. But this is basically, in this diagram, a function, because we have f of x, that is this, and we have x, that is the pH. is basically a function. This is the point on this axis, the starting point, and this is the slope, the angular coefficient, and we have x. So we are basically taking in consider the resolutions of the Nernst equation for the hydrogen line equations in the reactions of reduction, and we can appreciate how it could be solved, the Nernst equation, as a function in a Pourbaix diagram. So we can say that in this case the line of hydrogen is this one, with a slope that is minus 0.59 and a starting point that is obviously E0. But E0 is 0 volts, because we know that because we have described this 0 volts, because we have described this speaking about the reference electrode, the normal hydrogen electrode. So as a convention in standard condition, because here the pH is 0 also, we are able to set that this value is 0 as a convention. And this is the slope, and we can appreciate how the stability towards the oxidations, for instance, of hydrogen is decreasing. Why is decreasing? Because here, this is an equilibrium line. It's an equilibrium line that is able to separate the stability zone of H plus and H plus and hydrogen. So we can appreciate how increasing the pH, the resistance toward the oxidations is decreasing, whereas the resistance toward the reduction is increasing. So it's more easily to be oxidized and more difficult to be reduced. So if we want to do the same not only for this reaction, but also for the oxygen reduction reaction, so we have in this case, obviously in all these types of reactions are written toward reduction, so we have this plus this. Proceeding in the same way we have previously seen, so writing down the Nernst equation and so on, we can appreciate a result that is quite similar, but in which the starting point is versus this reference electrode E0 equal to 1.23 volts, but the slope is the same because the resolution is more or less the same. We can make this as an exercise. It's quite simple. We just needed to solve the Nernst, to write down the Nernst equations and solve it as previously done. And again, we have the same slope, but a different starting point. And so what it could be interesting here, that under this equilibrium line, we have the stability of this, or H minus. And above we have the oxygen. What does it mean? That here we have the stability zone of water. Here we have, when we are approaching smaller potential, we can promote the evolutions of hydrogen, and here we can promote the evolutions of oxygen if we are providing a higher potential with respect to this one. So basically this is important because it's the principle on which the electrolysis of water is based. If we will see this in a specific lesson, if we are applying a specific current in a Hoffman cell, in a Hoffman voltmeter, the specific structure in which the water electrolysis proceed, we are able to break down water and promote the evolutions of hydrogen and oxygen only if the potential difference applied is higher than 1.23. And so this is the starting point, the line of water that are always present in a Pourbaix diagram. And in this case, we have lines that are characterized with a slope. Why? The slope is not 0. It's a slope that with a specific number. And this is due to the fact that here we have both, and also here, an exchange of electrons. And so we have a we have a potential. And in this case, we have even the presence of H plus, or OH minus, so something that it could be connected with the pH. So both for what concerns the oxygen reductions and the hydrogen reduction, we have, in this case, that the resolutions of the Nernst lead to a function that can link the potential as a function of the pH. But this is not always true. So, okay, sometimes we can even have different sets of potential functions as the pH with different slope, maybe more sharply, maybe less sharply. In this case, for these two reactions, the slope is exactly the same. But sometimes we can even have a situation in which for a certain specific reaction, maybe it could be zinc, the zinc reduction. Here, this is, yes, a redox reaction. We have an exchange of electrons, but at the same time, no presence of H plus or OH minus is present. So here the potential is still remain always the same regardless the value of pH. And so we have just an horizontal line defining the equilibrium between the metallic zinc and the zinc 2 plus. What does it mean? That when we are in this condition, theoretically, if we are in water, for instance, if we are in water, so we are in this zone, water exists in this zone, if we want to introduce zinc inside, this zinc spontaneously it will try to be oxidized, because in water the zinc is stable as zinc 2 plus and not as metallic zinc, because this line, the equilibrium line, is here. And so we have the stability zone of zinc as zinc 2 plus in water, not zinc metallic zinc. In the case of gold, from the other hand, the gold is a quite huge noble metal, and we have a huge reduction potential associated with the similar reactions of reductions of gold. And so we can have the gold oxidized here and the metallic gold here. And so the metallic gold here exists in water, because water is under the situation. And what does it mean? That basically we are able to appreciate the stability of different species only in accordance with the Pourbaix theorem. So we are able to look at Pourbaix theorems and understand, okay, this system maybe is stable in this way, this species is stable in water. This is, for instance, extremely important for an electrophoretics process, or for, not for electrophoretics, sorry, for electroraffinery, electrowinnings and electrodepositions, for instance. Theoretically, even if this is not true from a synthetic point of view, but theoretically, the zinc cannot be deposited as metal zinc in water starting from this one, because it cannot exist as a stable metallic zinc in water. So, without make confusion, basically, now it's important to say that in a Pourbaix diagram we can have our horizontal line, so line associated with reaction in which the potential is independent of the pH, so the potential is constant. Obviously, it could be a little bit higher or smaller in according with the activity, because it's obvious that if the activity change, also the potential change in according with the Nernst equation. But basically, the line is always horizontal. We can have line having a slope when we are dealing with redox reaction involving the presence of H plus or OH minus that lead to a relationship between the potential as a function of pH, but we can even have sometimes lines that are vertical. What does it mean? Line in which the pH is independent of the potential. But what does it mean? What is the meaning of this? That if we are dealing with vertical line, this means that at this pH condition, we have a proton exchange reaction, not a redox reaction. Maybe when we're increasing the pH more and more, we are increasing the amount of H minus that can react with a certain species, leading to a certain product, maybe an oxide or an hydroxide. In this case, we are not looking at a redox reaction. So basically, we are just looking about the reaction involving a proton exchange and not a redox reaction. When we have a vertical line, this is obvious, we have no meaning of potential because we are not looking for a real redox reaction. So I hope that this is quite clear. But now I want to make one example. So in the next lesson I want to make one example. Imagine to build starting from zero an hypothetical Pourbaix diagram, the aluminum one for instance. And then let's make some example trying to understand how it's possible to read a Pourbaix diagram.